problem on meet in middle, which is given a set of numbers, can you find a subset which adds to x? This is a fairly known NP complete problem. That is, you are given a set of numbers, you are given a number x, you must return yes if the set contains a subset of numbers such that the sum of subset is x. That is, if some numbers of the set will add up exactly to x. Unfortunately, there are no basic approaches other than the 2 power n subsets. Take any subset, check the sum of the subset. If it is equal to x, great, we found a solution. But this could, in worst case, take n into 2 power n complexity. The complexity of the solution could be n into 2 power n. So how would we do this using meet in the middle? So I'm given a set S from 1 to n, and I define two more sets, S1, which is S from 1 to n by 2, and S2, which is n by 2 plus 1 to n. That is, I define two more sets, and I find all the subsets of S1 and all the subsets of S2, and I find all the sum of subsets of S1 and all the sum of subsets of S2. Now, by doing so, my claim is, if there exists a solution, I can say that there will exist an x in S1 and y in S2 such that x plus y, if there exists a solution, there will exist an x belonging to x1 and y belonging to S2 so that x plus y equal to x. Is anyone not clear with this claim? That is, I divide the set into two halves. I take all the subsets of first half, I take all the subsets of second half. I'm not going from a polynomial to, that is exponential to polynomial. I'm still enumerating all the subsets, but I'm enumerating subsets of a much smaller set, a set of about half the size. So is everyone clear with the idea that there will always exist if there exists a set S, so if there exists a sequence such that it adds to x, there will exist a x and x y such that x plus y equal to a required number capital X. Please note that 0 is a member of this and 0 is a member of this. So if it is entirely contained in S1, y would be 0, and if it is entirely contained in S2, x would be 0. Is everyone clear with this idea? So we have essentially reduced the problem to given 2 power to, let's say, we'll just take 40 for example. So we are given two arrays of size 2 power 20, and let's say I will now rename these two as S1 and S2. So we are given two arrays of size 2 power 20, and we must find whether there exists a number x plus y equal to x. Brute force way again would be for every element of x, for every element of b, check for every element of a, for every element of b, check whether ai plus bj equal to x, which would take 2 power 40. So we have not made an improvement in that way. So what can we do to make this easier? We could sort. So the approach is now fairly simple. You can just sort A, sort B. After sorting, you can either use a binary search, which is for a given element of A, I find, because B array is now sorted. So the problem reduces to, I find some element in B such that A plus B is equal to X. That is, I try to find X minus AI in B, which reduces to the binary search on array solution that I said earlier. But you can of course do this. So the solution, complexity of this solution would be, if I sort and binary search, sort plus binary search, complexity would be theta n log n. For every element of A, I'd be doing a log n complexity binary search on B. So sort, and this would be n log n. Actually, this is a fairly good solution and which should run in reasonably good time. This is 1 million, this is 2 power 20, and this would be another 20. So this would probably take 1 second to, this would be 1e6. This would be 1e6 and 20 would be 2e7. 2e7 is fairly small, so it can run at reasonable time. But you can reduce this further and make it theta mod A plus mod B by using what is known as a two-pointer technique. How to define that is, let's say I have my array A here, I have my array B here. Assume I have one pointer here and one pointer here. That is, I iterate over each element A, and okay, so I just check what the sum of this plus this is. If it is greater than x, I can reduce this further, because for any A, if I, instead of this, if I use any A after this, it would only lead to a greater sum. So I can, so essentially by moving these pointers, I'd get a solution which is mod A plus mod B. the details are fairly simple to get. So yeah,
sorting the array.
right.
Complexity will change.
Yeah, complexity.
Okay, all right. Yeah, complexity won't change, but assume means this is a technique which is generally used in programming contests. So, of course, if you're sorting, you can of course you do a binary search. Okay, next slide. Yeah, next. Yeah, please. The problem that you could try to do is maxi set on Spoj. Please note that subset sum problem is a fairly basic problem that I discussed now. That is, now for meet in the middle, you could probably like I could give another example in which I have a state S1 and another state S2, and I must check whether I can reach from S1 to S2 in X steps. So if I generate a complete binary tree, and let's assume that the branching factor is B, the number of nodes in this tree would be B power X. That is, I'll do a BFS until X. So the maximum number of nodes in this tree could be B power X. Right? So instead of that, if my state space is symmetrical, I could do something like this. Means what meet in the middle does in a graphical way is I search B to B power X by 2. I search from final state to B power X by 2. B power X by 2, B power X by 2, and this would give you the solution. Means this is kind of the graphical way of understanding what meet in the middle is. You can try these. This problem is essentially what subset sum is. It was asked in TCHS, and then there is split and merge game is a proper meet in the middle, something like what I said, and you can also do maxi set. We are not unfortunately able to add all problems of Spoj to the contest because of some some problems are not addable to private contests. So in which case we have added it in the bottom as a link. So you can also check the bottom links and try to get those accepted too. What is the next slide? Okay, my final topic for the day is any doubts in meet in the middle? Yeah. This one? Alright, so let's just assume that I must find whether S2 is reachable from S1 in X moves, right? So let's just assume that it's a board game. What I'm having is I have a board like this, and I have some checkers at some point. I can move each checker one position at 4 positions, and okay, let's say there are 2 checkers. I can move each checker in 4 positions. So for each state, there are 16 possible moves, right? So 8 possible moves, 8 possible moves. So from each state, the branching factor is 8. So if I compute the BFS tree for X distance, I might probably end up with B power X nodes, right? So instead of that, please note that if I can move a check, I'm just talking about orthogonal movement. So if I can move a checker from here to here, I can of course move it back. So I go from final solution to some middle solution. I go from initial solution to some middle. I generate tree and from B to Bx by 2, this to Bx to Bx by 2, and then if there is a common node, great. Otherwise, I'm not doing it right. That is, I cannot reach it in next node. Final topic is randomized algorithms. This is fairly new and is a fairly nice technique. That is, you can probably get problems accepted on this. The idea is code length will be very, very short. A hard part will be proving that it will work. So, easy example is randomized quicksort. Does everyone know randomized quicksort, where pivot is chosen in random? Anyone who's not clear with randomized quicksort? Yes.
Do you want to take the coffee break now?
It's almost done. Okay. This should be enough. So this is the last topic, just in case you're wondering. So randomized quicksort is an example of a randomized algorithm. It's used extensively in coordinate geometry because geometry has a lot of properties which make writing worst case solutions impossible. Like if you try to write a convex hull problem in which, like, one problem you could try to do is n points such that the number of n integer coordinates such that the number of points on the convex hull is large. It is fairly difficult to generate such points because it is not geometry has a lot of properties because of which it becomes difficult to generate worst case input. So randomized algorithm works very well with coordinate geometry. We will have a session on coordinate geometry after the tea break. So there are two types of randomized algorithms, Monte Carlo and Las Vegas, which is this all just textbook stuff. Monte Carlo means running time is fixed, but correctness is probabilistic with a very low probability, but it's probabilistic. Example is primality testing. Well, Las Vegas algorithm is running time varies, but it's always correct. Randomized quicksort. It's a randomized algorithm. Las Vegas could take worst case n squared, but the probability of worst case n squared is very, very, very low. Okay, next one. Okay, so just to give an example of how good randomization is, I'll give you a problem from PKU. PKU is a Chinese online judge. You can check the problem here. Okay, so you are given 3 n cross n matrices A, B and C, and you must compute whether A cross B equal to C. Easiest way, you can just multiply A and B and check whether it's equal to C. But this problem is designed in such a way that an n cube solution would not work. Okay, matrix multiplication is n cube. So an n cube solution would not work, but you still have to check whether A cross B equal to C. Yes? You're saying something? So yeah, any ideas on how to proceed? I can tell you that n cube times out, and what it asks to check, of course, can be naively done in n cube, but unfortunately n cube times out. All right, so please check this problem, and yeah, Winky, next slide. So the idea that you use is you choose a column vector x, column vector, that is column vector means an n cross 1 column vector x, and you check whether ABX equal to CX. If AB equal to C, then by the left multiplication rule, ABX would be equal to CX for any x in the space. So if this is true, then with a very high probability AB equal to C, and it's very, very less probable that AB is not equal to C. So if I choose x, I can choose x from x as random elements, but even if I choose x with elements only 0 and 1, I can prove that there is 1/2 probability of a false positive, which is great. So if it's 1/2 probability, if I do 10 iterations, it's 1 in 1,000 chance that I'm still working with the wrong solution. So let's say I do, but of course I would not be choosing x from 0 to 1. I'd be choosing x in the real number in the integer number range. So the probability is fairly low with just 1 iteration. So in n iteration, in just 2 or 3 iterations, you can be fairly certain that AB equal to C or AB not equal to C. You could try to get this problem you can probably think that, in case you're not clear, you can think that the complexity of finding ABX can be found as BX and then A into BX, which will be theta n squared, because BX would be a column vector. Matrix into a column vector would be n squared, and CX can also be found in theta n squared. So n squared into number of iterations would be how much would be the number of steps you need to solve this. Yes, next slide. You can try to get this problem accepted, which is probably which the lines of code would probably be fairly small, so you could try to get this problem accepted.